in Monty Python terms now for something completely different. We've seen the talk with some lots of code in it, no code in this one, about systems thinking. It seems to me if you ask 100 people what is systems thinking, you'll get 100 different answers, because it's something of an umbrella term for lots of subtopics underneath it. This is the definition I use. And I can say from personal experience that the idea of systems thinking and the things that I now think I understand better than I did before didn't come naturally to me. And I think that's something that's general for human beings. We haven't evolved to understand things where the cause and effect go on over a long period of time. It's just something we've not evolved to do. Lots of quotes from lots of books that were influential to me on my journey. This one's from Peter Singer. He wrote a very influential book in the 70s, Fifth Discipline. It is an axiom that influences both cause and an effect. And again, there's the aspect of time. Some of you may have come across this book. I love this quote. To say that certain events are causally connected is a clumsy way of saying they are features of the same event. Yeah? And there's lots of quotes that aren't from books that aren't software related. I've tried to draw it back towards software examples and quotes from actual software books. So some of you I know will know this guy, Jerry Weinberg, who's very influential for me. He was the project manager for Project Mercury, which was the project before the Apollo missions. They had to basically get lots of technology in place that didn't exist before so that they could get sufficiently accurate timing on Earth. It was the first time they needed atomic clocks, for example. This is called the causation fallacy. It's actually two fallacies. Every effect has a cause, so the first fallacy is the word A, that there's one cause, and that's not true. There's always multiple causes, it's just we like to home in on one of them a lot of the time. And the second part of the fallacy is that we can tell which is cause and which is an effect. And again, once you start to understand the passage of time and how these things come back and loop on themselves, that's not true either. So an example I love is this example. It's a fairly self-evident truth that if we have defects in the code, that's going to cause lateness. Hard to argue with that, okay? But if we keep an eye on the direction of the arrow there, and we try that one, what about that? Yeah? I think that's equally true. So do defects cause lateness, or do lateness cause defects? And the answer is yes. They dance around each other. Again, we can't really tell what's cause and what's effect. It's something that happens dynamically over a passage of time. So an example that I call Scrum buses, which again is a slightly less obvious example, if you like, is having 4 buses. Imagine there's a route, a circular route, and there's 4 buses going around on this route. And they all start equidistant apart at the 4 sort of 90-degree points of that circuit, yeah? It's inevitable that at some point one of those buses is going to have less people to pick up than the average, let's say, okay? So what happens to that bus? It gets faster. It doesn't have to stop so often. It gets nearer to the bus in front of it, right? Now, as it gets nearer to the bus in front of it, is it likely to get more passengers that it needs to pick up or less? Less, okay? So if you don't constrain that system, you will naturally get the buses lumping together. They start off equidistant, 4 of them, 90 degrees apart. They will start to lump together, and you'll get 2s, okay? Because it's not just a forward effect, it's a backward effect. If this bus is getting nearer to the bus in front of it, it's getting further away from the bus behind it. That means the bus behind it is going to pick up more passengers than it should, on average, and that means the bus behind it is going to get nearer to it, okay? So it starts off with 1s and it becomes 2s, and what happens then? The 2s start to clump together exactly the same way, and it's just the way the system is designed, right? The systemic effect. It's the relationships between the buses that is having this effect. So how does this relate to Scrum? Scrum says you have fixed duration intervals, and that's a critical constraint. Okay, in terms of the bus analogy, if the bus gets to the stop, yeah, and there's not many people to pick on, to take on, it stops and it waits. Okay? It doesn't carry on until it's the right time for it to carry on. And then you have constraints in the system that negate this effect of things naturally starting to lump together. Okay? And if you don't do this, what happens is you get waterfall. Right? Waterfall is exactly this idea for software development, where things that should have been 1, 2, 3, 4, 5 iterations all lumped together, and you get one, maybe, after a long period of time. Okay? That's why when you wait for buses, there's none, and then suddenly 2 come along. Okay? Now you know what happens. Feedback. This is a crucial part of this whole dynamic system dynamics. So a quiz. Can you name the 4 XP values? And I've sort of used a pointless style question here. I don't know if anyone watches Pointless on telly. My son loves it, so we watch it together. Can anyone figure out what the 4 values are? I'll give you a clue. All right? So the bottom one is feedback. Communication. Simplicity. And the one that people never get. People are really surprised when they learn what the 4th value is for XP. Courage. Courage. Okay. So we're looking at feedback particularly. This is crucial for me because it's something that unifies both XP and Scrum. This is some quotes from the Scrum Guide, just pulled out. And people look at lots and bits and bobs inside the Scrum Guide and XP as well, but what they often fail to do is look at the underlying values which tell you, if you read them carefully, why it was built the way it was built, okay? Why it was constructed and designed the way it was constructed. Why do we deliver products iteratively and incrementally? So that we maximize opportunities for feedback. That's what it says. Okay? What happens in the sprint review, the presentation of the increment, they use a capital I, it's the term, is intended to elicit feedback and foster collaboration. Okay? This is, again, a very influential book for me. A guy called Jon Jagger wrote a book called The Systems Bible. Some of you nodding, you've come across it. Okay? When I read this, you know how sometimes you read a book and it's the right thing at the right moment, and a bell goes ding in your head, right? Yeah? This was a ding for me. Just calling it feedback doesn't mean it has actually fed back. So again, there's that time aspect. Yeah? The information that's coming out from that end of the system is coming back again and being fed into the system earlier, as it were, in terms of the cycle, to cause a change in direction, potentially cause a change in direction. These quotes coming up aren't from this book. The ones further on now are from a talk I was fortunate enough to see Jon Jagger give in London, hosted by Tom Guild a couple of years ago. And it really, to me, emphasised this point about the difference between man-made systems and natural systems, biological systems. Yeah? The amount of feedback we have in even the biggest, or the best, if you want to use that phrase, man-made systems is just absolutely tiny in comparison to biological systems, which, as it says, have integrated total unification through feedback. They have a single purpose, right? Compared to a frog or a salamander, our biggest man-made systems seem like simple wind-up toys. That really spoke to me. Bringing it back to software again, just for a moment. Ignoring feedback merely, this is again Jon Jagger, merely means the system will eventually experience a massive unpleasant surprise, rather than a small unpleasant surprise. Yeah? Now, we can start to tie some things back together again, because we know that it's very hard to tell cause and effect. We think something's a cause and its effect and vice versa. So using that idea, if you experience a massive unpleasant surprise, it's telling you something, right? It's telling you you've been ignoring feedback, right? You just have to figure out what it was. Jerry Weinberg says exactly the same thing. It may look like a crisis, massive unpleasant surprise, but it's only the end of an illusion. That's what he says. I love that quote. Some slides on change. Then about blood sugar. Donuts are a prime source of sucrose. Yeah, they're mostly sucrose. And if you eat a donut, the amount of sucrose in your blood goes up. And that's bad, because if you have too much, it causes hypoglycemia and you die. Okay? But of course, the body doesn't let that happen, because the pancreas senses the increase in sugar in the blood, and that causes extra creation of insulin that goes into the blood. And the liver and the muscles sense the increase in insulin in the blood. And what does that cause? It causes the conversion of glucose to glycogen, which reduces the amount of glucose in the blood, and that's good because it avoids hypoglycemia. Okay, except no, it's bad because if you don't have enough blood sugar, you get hypoglycememia and you die. But fortunately, the pancreas senses that too, yeah, and it causes the creation of extra glucagon to go up. The liver and muscles sense the increase of glucagon, and that causes here the glycogen to be converted back to glucose. Yeah? And that's how the body maintains the glucose, the blood sugar level, at really, really fine tolerances. Yeah? This is why we live. And this is an example of what's called Le Chatelier's principle. It's a great principle, it's just a shame it had such an unpronounceable name. Systems tend to oppose their own proper function. And again, when I was younger, I didn't really crucially understand this idea of the word proper. And Hubert helped me out many years ago. And again, to quickly go through it again, this is, if you think about it in the dynamic sense, the system opposing its own proper function. It's proper that the blood sugar goes up and that there's a system to bring it down, but the same system, the other half of the system, opposes that mechanism to bring it down because we have to then bring it back up again. And there's a balance that it's constantly trying to maintain, again, in that dynamic sense. Okay? That's called Le Chatelier's principle. This is, again, another influential book for me. Really helped me understand that example of the blood sugar. All change can be understood as the effort to maintain some constancy. So all that dynamic change, the pancreas and the liver and the muscles are all causing, and the glucagon and the insulin and all that kind of stuff, okay? Massive effort. You don't see, it's sort of behind the scenes, just to maintain the constancy of that glucose level, the blood sugar level, okay? And all constancy is maintained through change. Again, there's that duality. Yeah? Going further, again in terms of the biological analogies, because it really speaks to me, the battle over food and territory between two species is only half the story. The battle itself is a means or a process of generating, maintaining, and stabilizing the ecosystem over time. If this battle didn't exist, yeah, there would be no pressure on the system to enable it to sort of adapt when it needs to adapt. Okay? Not quite sure about the quote there. I think it's from that book. So, again, it spoke to me, evolution is always co-evolution. That really spoke to me when I first read that. What involved is not simply survival of the fittest, but survival of the fitting-innest. Right? And that changes over time. So again, a little example. We've got a bat with its sonar, and it's finding the moths. What happens if there's a mutation and it's able to generate a more powerful sonar? Is that always a good thing? Well, hopefully you're realizing now, no, it's very rare that something's always a good thing. There's the duality to consider in terms of the cycle, okay? Because if the bat is issuing a stronger signal, yeah, then the moth can hear it from further away, right? You have to consider it from the other side as well, right? So again, there's that delicate balance. And just to emphasize the point again, there's the original signal before the mutation, and this is how big the moth's ears have to be, for example, to hear the signal to be sufficiently far away to not get eaten by the bat. And there's obviously some moths with better ears and some with worse ears, but there's a balance, and some survive and some don't. That's just the way the system's balanced. But suddenly, just look at the ears there, right? You see? Okay, yeah? Now we've changed the nature of the system. It's always a system. There's always the dynamic interactions going on. Okay? A few words on Slack. Do you remember that little puzzle? Yeah? Imagine if there was a red piece in there, a 16 in there, right? A red 16 in there. Wouldn't be much of a puzzle, would it? Right? And bicycle chain. If it's too tight, it doesn't work. If it's too slack, it doesn't work either. Okay? There's a slack that gives it just the right sweet spot. Have you come across this book by Don Reinerstein? Highly recommend it. It's about capacity. How much are you overloading the work with too much work in the system? The capacity is this, and there's this much work. Okay, that's a very bad thing. Moving from 75% to 95% utilization increases variability by 25 times.
Does it all depend very much on the kind of thing you're building? I mean, if you're moving a car manufacturing plant from 75, a conveyor belt, from 75 to 95% utilization, does that still apply, or does that just apply to more variable processes?
I mean, I don't know in terms of the maths whether it covers all possible, what's the word? Whether it's a normal distribution or Gaussian distribution or all the distributions that might occur for what's happening. You'd have to read the book and perhaps email Don to find out. But my reading of the book from when I read it, which wasn't that recent, was yes, it's fairly robust in the same kind of way that Little's law is robust. Okay, it's pretty much over all distributions. Yeah, and you know this instinctively. It's just when we see it with maths like this, it's a little bit harder to see. If you do it with utilization, for example, of a motorway, right? If the motorway is at 75% capacity, that's probably the best you can do, because the flow that you've got across a certain stretch of motorway is as good as you can make it. You've got quite a lot of people on the motorway, but they're not sufficiently tight together that the braking of one causes the other one to stop and the whole system jams up. Everything is flowing through the system, okay? But we all know that if we allow more and more cars to come on without constraint again, okay, and suddenly we get to 95%, the whole system tips, doesn't it? Right? And suddenly you're on that orbital car park that we know as the M25, right? Yeah. It's exactly the same idea. Yeah. The best you can do in many situations is have a system that is at 75% capacity. If you're a manager and you think, okay, I've got 4 developers and it seems like all the time one of them's slacking off and not doing anything, that's maybe the best you can do, right? That's what it's basically saying. You have to have some slack in the system to allow the system to adapt to the changing situations as they occur, right? Assuming you've got a complex system. If you've got a trivial system, you've got no problems, right? And again, all the software gurus say this. Eric Ries, a lot of buzz about his stuff just last year. That which optimizes one part of the system necessarily undermines the system as a whole. Again, this optimizing of one part without thinking of the whole is exactly what nature doesn't do. Yeah? Animals have a single purpose. And very often when you work for an organization, it seems to me, you don't get that feeling of there's a single purpose that that organization has. Okay? And this is just another way of thinking about it. You've probably heard this as the whole is greater than the sum of the parts. Okay? This is just another way. You have to think about this. Optimizing this, maybe 75% is as good as you can do. Don't think about this. Okay? We don't want everyone sweating all the time so that they're knackered. Okay? We don't think faster if you crack the whip harder. It just doesn't work that way, right? Anyone know what this is? Plutonium-239. What happens if you add 2 kilograms of plutonium-239 to 3 kilograms of plutonium-239? The answer is you get 5 kilograms. No surprise. What happens if you add 5 kilograms to 5 kilograms? Right. Yeah? It's not just the sum of the parts. Right? There are interactions between the parts that cause an effect that is not predictable, if you want to put it that way. Okay? Lovely example, I love this one. How many flowers should a bush have? It seems a no-brainer initially that it's as many as possible. More is better. Attract more insects. Okay? More pollination. There's a downside with that though. Can anyone figure out what it is? I couldn't figure it out. Can anyone figure it out?
To block the light from the...
No.
Because you have to be visited more than once. Every flower has to be visited at least by 2 different bees. Right?
Go on, why?
Because otherwise it can't spread the pollen from one flower to the next.
Oh, not quite.
Well, if you have more flowers than you have bees, then you're wasting energy as well.
The problem is, if you've got one bush with lots of flowers on it, you're encouraging the insects that visit to visit this flower on the same bush, and then this flower on the same bush, and then this flower on the same bush. And you don't get cross-pollination. Okay? And so nature knows this, and you'll find there's a sort of sweet spot, sometimes called the Goldilocks phenomenon, right? It's not necessarily the case that more is better, once again. There are systemic effects, there are dynamic effects that for me are not intuitive, and this is stuff you have to learn. So to finish off, the law of unintended consequences is another way of talking about the same thing. This true incident I think it was in the 60s, the government in Calcutta had a problem with cobras. There was lots and lots of cobras, and they decided it was a problem. So to fix this problem, they issued a $1 bounty for every dead cobra that was brought in. True. And for a while it worked beautifully, and the number of cobras went down, and then what happened? No?
People started breeding cobras.
People started breeding cobras. Right? Natural part of an adaptive system, okay? They caught some cobras in the wild, they didn't kill them, they let them breed, get to the right size, because they had to be a certain size before they would get the $1 bounty, chop their head off, come in, claim the $1, lovely jubbly, okay? Government eventually figured out what was going on. What did they do? Stop the $1 bounty. What happened? They released all the... They didn't want to kill the cobras. They're only doing it for the money, right? They released all the cobras. Net effect, way more cobras than when they started. Okay? This is called... There's a really great website called the Museum of the Law of Unintended Consequences, where you can read about lots and lots of examples of this, true examples of this idea. And you have to be so careful, because it's easy for the way the system evolves over time to have this effect, that you intend to cause one thing, to have one effect, and you have exactly the opposite effect. The opposite effect, okay? It's really, really easy for that to happen, so be careful what you measure. Okay? And that's all I have to say. Thanks very much.